Have you ever tried to navigate a massive enterprise wiki, only to find yourself completely lost in this maze of disorganized folders, sluggish load times, and just intimidating raw code? It's a total nightmare in large organizations. But what if we could take that clunky experience and completely transform it into a sleek, lightning-fast application? Well, welcome to this explainer. Today, we're diving into a really fascinating blueprint for building Azure DevOps Docs as code. We're going to look at the huge promise of a modern Docs as code architecture, how it actively shields everyday users from complex syntax, and how the whole thing eventually evolves into this incredible, cutting-edge serverless powerhouse.
So here is our quick roadmap for today. We'll be covering Section 1, the Docs as code dream, Section 2, virtual routing, 3, Monaco magic, 4, parsing with AST, 5, bypassing restrictions with swaps, and finally, 6, the serverless pivot. Let's jump right in.
Section 1. The Docs as code dream. Shielding users from complex syntax. So to actually shield users from all that raw code, we build out front-end features that make this feel like a totally seamless everyday app rather than some hardcore code editor. The main goal here is to create a visual interface that entirely hides the raw YAML and Markdown from non-technical users. First up, we start with visual front matter. Instead of asking someone to manually type out YAML metadata like area paths or story points, we just give them a React form with simple drop-downs. Easy, right? Then we bring in an interactive drag-and-drop hierarchy. Users can just visually model predecessor and successor relationships right in a tree controller without ever touching the actual underlying wiki structure. And lastly, we have auto-compilation. Behind the scenes, the front end takes all these visual inputs, the forms, the dragged folders, the hidden IDs, and it automatically compiles them into perfectly formatted Markdown with the YAML front matter totally hidden away. It is beautifully simple for the user.
Moving on to Section 2, virtual routing for performance, speeding up enterprise wikis.
Now, having a pretty UI doesn't really matter if your backend completely crashes trying to load a massive wiki tree, right? Think about that agonizingly slow load everything approach where the system is sweating, trying to pull down thousands of documents all at once. We replace that completely with virtual routing. It's basically a smart, lazy load approach. We add a simple dropdown in the React UI where users select a high-level branch or a specific path. When they click that, the backend uses API pagination, specifically the recursion level parameter set to 1 level in the Azure DevOps REST API, to fetch literally only its immediate children. Then, when a user expands a folder, a super lightweight background request grabs just that specific folder's contents. This keeps the UI incredibly fast, no matter how massive the enterprise wiki actually gets. Section 3. Client-side Monaco magic, bringing the IDE right to the browser. To pull this off, we integrate the Monaco editor, which, fun fact, is the exact same engine that powers VS Code. We drop that straight into our Vite React app. But the really crucial point here is how we handle validation using an LSP, or Language Server Protocol. Typically, getting real-time autocomplete and validation requires a persistent backend connection. But by installing the Monaco YAML package, we can actually run the YAML language server right inside a browser web worker. We make an initial API call to fetch valid Azure DevOps area paths and tags, dynamically inject them into a JSON schema, and just pass that straight to Monaco. The result? You get instant, real-time autocomplete, validation, and hover descriptions entirely on the client side. We completely eliminate the need for those complex backend WebSockets. It's a huge win.
But we have to remember, Monaco is fundamentally a code editor, not a standard rich text box like Microsoft Word. So to keep our non-technical users happy and comfortable, we add an industry-standard snippet injection toolbar right above it. This gives users that familiar, friendly formatting ribbon. Want a task list? Just click the button and it drops the exact right Markdown syntax directly into the editor. If you highlight some text, select C# from a dropdown and hit code, it instantly wraps it in proper code blocks. It gives them that what you see is what you get experience while maintaining our pristine Docs as code architecture underneath the hood.
Section 4, AST, parsing the Markdown, the blueprint behind the text.
Here's where we get into the really cool mechanics. We use an abstract syntax tree, or AST. Think of an AST like a blueprint for a house. When you look at a house, you just see walls and windows, right? But the blueprint shows you the exact structural nodes, the plumbing, the electrical routing, the load-bearing walls. And AST does the exact same thing, but for text. It allows us to take raw Markdown text and convert it into a traversable structure, specifically a Markdown Abstract Syntax Tree, or MDAST. Because we have this structure, specific elements can be easily found, manipulated, and swapped out without breaking the entire document.
So let's walk through how this builds our pipeline step by step. Step 1, we use a library called gray matter to extract the YAML metadata, so things like tags and explicit predecessor IDs, cleanly separating it from the main Markdown body. Step 2, we tap into the unified.js ecosystem, specifically using remark parse, to generate that Markdown abstract syntax tree right from the raw text. And step 3, we use unist util visit to physically walk through that tree. This is powerful because it lets us target specific sections dynamically. For instance, we can hunt down a heading node that explicitly says acceptance criteria and easily extract absolutely everything nested underneath it.
But here's where we hit a pretty major roadblock. We want to convert the checklists in our Markdown into cohesive, interactive checklists inside the Azure DevOps rich text fields. But ADO actively strips out standard HTML checkboxes. They do this to prevent cross-site scripting attacks, which totally makes sense. But it leaves us with a big question. How do we bypass Azure DevOps HTML restrictions to actually get our checklists?
Section 5. Bypassing restrictions with swaps. The Unicode magic trick.
This is where we pull off a clever little magic trick to outsmart the system. We intercept the checklist nodes in the AST while they're still just raw data points, specifically looking for list nodes where the checked Boolean is present. Then, we execute what we call the Unicode swap. We mutate these nodes into standard HTML list items, but instead of using a prohibited checkbox input tag, we prepend them with Unicode characters. We use very specific hex codes to simulate empty white squares or green check marks. Because these are just standard text characters sitting inside an allowed list item, they totally survive the HTML conversion process and they render beautifully right inside ADO's rich text fields.
And the coolest part is we don't stop at just the visuals. We implement what's called a dual task strategy. Step 1, like we just talked about, is mutating the AST for those visual Unicode checklists so they look great in the acceptance criteria field. But step 2 happens at the exact same time. We extract the literal text of those tasks into a JSON array, and we automatically generate mapped child task work items via the API. So the exact same parsed data visually updates the acceptance criteria and creates actual real child tasks behind the scenes. It's incredibly efficient.
Now, up until this point in our explainer, we've basically been talking about sending all this data to an Express backend to do the heavy lifting. But then, there's a dramatic architectural plot twist in the source documents. A single, powerful directive is given. Turn off the back office.
Section 6, the serverless client-side pivot, eliminating the backend infrastructure.
Look at the massive contrast here. In the old way, using the Express backend architecture, our front end was really just a pretty face. It had to send all the Markdown over to a Node.js server, which then processed the AST, mutated the HTML, and fired off the API calls. But the new serverless client-side approach completely changes the game. It relies on the fact that libraries like Unified and Remark are isomorphic. That simply means they can run perfectly fine directly within the browser's own JavaScript engine. So we literally don't need the Node server at all. We can just turn it off.
By migrating the compiler directly to the front end, we massively reduce our infrastructural overhead. Just look at what's happening entirely in the user's browser runtime now. AST parsing happens right in memory. The Markdown mutation and Unicode swaps, done in the browser. The construction of the complex JSON patch payload, in the browser. The direct API orchestration communicating with Azure DevOps, all of it is happening directly from the Vite React front end. We've completely shifted the entire burden of this complex docs as a code pipeline right onto the client side.
And how is this highly sophisticated evolution actually orchestrated? Well, through agentic execution workflows. The source documents detail this master plan made up of hierarchical, step-by-step Markdown documents. But these aren't just your standard instructions for a human developer. They are explicitly designed to be ingested by an advanced agentic AI, which the docs refer to as running in anti-gravity mode. This AI agent actually reads the hierarchy, sets up the browser, scaffolds the Vite app, configures the complex file system access required for the web workers, and even runs standard test-driven development loops to ensure Azure DevOps API compatibility. It's literally an architecture designed to be built by an AI agent. Mind-blowing, right?
Which leaves us with this final, really provocative thought. We've just seen how a complex, multi-layered back-end process was completely replaced by isomorphic libraries running directly in the browser. So I have to ask you, if the modern browser can handle full AST parsing, run real-time language server protocols, and manage complex API orchestration completely on its own, what other back-end systems are ready to be turned off? Think about the heavy servers you rely on right now. How many of them are just sitting there waiting for a serverless client-side pivot?
Thank you so much for joining me on this explainer. I really hope this sparks some incredible ideas for your own architectures.